Next, we have the topic of line integrals. So, line integrals, there are two types of line integrals. There is the scalar and vector varieties. They are related to one another because a vector line integral is simply defined to be a very specific type of scalar line integral. But we'll start off with the idea that in this section, we're going to be integrating over some path. This path can be in any dimension, but I will be speaking as if these are in 3 dimensions, just for generality. So when you have a path in 3 dimensions, you want to go ahead and have an orientation, so what direction is it being traced in, and you want to go ahead and have a domain for your parameter. So whenever we want to integrate over a path, we want to have a parameterization and a domain for that parameterization. Together, we can then use that to evaluate these. Let's start with a scalar line integral. What is a scalar line integral? A scalar line integral effectively is the area under a surface. Now you might be thinking, isn't there only volume under a surface? Well, not if you look at it from this perspective. So here, let's go ahead and, for the sake of drawing, I'm going to draw a function z equals a function of x and y. It's easier to do this. So imagine I've got some surface here. Okay, so there's some surface. Oops. And I'm going to go ahead and pretend it does something like that. Okay, so there's some surface. And now imagine in the xy plane, so let's go ahead and just imagine drawing that xy plane. So in the xy plane, imagine that there's a path. Starts at a point P and does some loopy thing to some point Q, and we trace it in that orientation. Well, then what you can do is imagine taking every single point on here and lifting it up and looking at its image on the surface. And that's going to create its own path on the surface. Not only that, but this kind of creates this curtain. This curtain. And this curtain has an area. So this is the area underneath of a surface along a path, and that path can be curved in the domain space for the function. So this function that creates this surface here, this function has a domain of 2 variables. So the path that I drew here, this path is in the xy plane. There's a reason why I drew it this way and I didn't draw it using a function of 3 variables, because I can't draw this because the graph lives in 4-dimensional space. So that's conceptually what it's telling you. So what we want to do here is, when you see this, what we want to think about here is this ds is this, the magnitude of the derivative. So you start with a path C, you go ahead and you come up with a parameterization for it. Once you know your parameterization, you then find your derivative and take the magnitude of it. That goes there. You replace x, y, and z with whatever your parameterization says the x, y, and z components are. So one thing that's usually helpful, and a lot of times gets asked, is what is ds? ds, you can think of it as the magnitude of the derivative, dt. Now to me, that's exactly what this says. But to be much more explicit, that's what we have. So if you see ds, it means it's a scalar line integral, and you would compute it in this way, where your a and b come from your domain for t. Okay. If your function is just 1, then, so that means you're doing something that looks like this. That means what the result of this integral is numerically, it's going to represent the length of that path C. Okay. Vector line integrals. Vector line integrals are a little bit harder to explain conceptually. There is a video that's posted that attempts to do that in a little bit more detail. I will not go into nearly as much detail here because you do not need to have a purely geometric interpretation of what a vector line integral represents to do well in this class. But I know that it's useful for some people to have something tangible on which to stand. So, what is a vector line integral conceptually? Well, let's take a look at this. F.dr. What's the definition? The definition of a vector line integral is this. So they're defining a vector line integral in terms of a very specific scalar line integral. So really this f dot t. So this is by definition what is dt. So if C is a path that's parameterized by r of t for t between, let's say, a and b, then capital T, if we remember from chapter 13, capital T is the unit tangent vector. So that's the derivative divided by the magnitude of the derivative. That's what capital T is. We're not going to really use this in here right now for this explanation, but I'm just wanted to recap what capital T is. It's the unit tangent vector. So if our path C is this kind of loop, then at this point right here, the unit tangent vector is right there. So it has a length of 1. It's pointing in that direction because as we imagine moving along the curve, in that moment, that's the direction of our line of sight. Imagine this is a roller coaster track. Where are you looking? In that direction. All right. So, taking a closer look here, what exactly is f dot t? Well, f dot t, because t, capital T, is a unit vector, this right here is the scalar component of projection of f projected onto t. So if we go back to our path here, we're at a point. At this point, our unit tangent vector is this. The vector field at this point might be, maybe it's pointing like that. So let's say this is the vector field. So it's the same vector field that we started with. And we're just looking at it at a specific point. Now this integral here is going to effectively figure out what this quantity is at every single point on our path C, and then multiply it in a sense by this, in a certain sense. But what's really important here is we're trying to chip away what is this. Well, I mean, this ds is actually telling us like a little length here, kind of. It's a little bit of a length. It's a little piece of this curve. That's what ds is. So you can think of this as a small arc length of this curve C. So what this f dot t is doing, it's the scalar component of projection. So we can take a look at what is the projection of this vector onto this vector? Well, imagine extending this out backwards and seeing where the tip of this vector lines up. It would be right here. So this right here, we would have to take this vector t and multiply it by a negative number to flip it, and then this distance here is a little bit longer than this distance here. So this number, based on this picture that I have, would be a negative number bigger than, so it's some number that's less than -1. So like -1.5, -2, something like that. It's going to stretch this vector a little bit, so it has to be bigger in absolute value than 1. It's going to stretch it, not shrink it. So that's what that is. It's the shrinking or stretching factor for our unit tangent vector to make it line up to the tip of the vector field f. So in a sense, this is a number that tells us how much the vector field is pointing in the direction of motion. If it's a negative number, that means it's pointing opposite of our direction of motion. Not literally exactly opposite, but it's certainly, if you draw a perpendicular to this, it's on this side. So anything on this side would be a negative contribution. Anything on this side would be a positive contribution. And if it's orthogonal, then the contribution is 0. So that's what so that's ultimately what this is. So we're really figuring out what that amount is at every step along the curve, and then we're multiplying this by a little amount. So ultimately, this is telling us the area underneath of a surface, just like this. But that surface here is defined to be this. So like z equals f dot t, kind of. Very informally, but that's what it's doing. Okay, so to compute this, we don't actually in practice use this middle part to compute them. That is the definition of it, but in math there's usually this tension we're trying to balance. In math, on one hand, we want definitions that are useful and flexible enough for us to prove things, so we want them sufficiently general. But when it comes to actually computing things, sometimes the ultra generalized and abstract definitions don't provide us with enough computational leeway to actually do a lot of real-world problems. So that's where this comes in. This is a lot more restricted than this notion, but it is how we're going to start to calculate these things. So you have your path, you have it parameterized for t between a and b. So your a and b go here. You replace each x, y, and or z in your vector field with whatever r tells you x, y, and z is equal to. And then you dot with the derivative. There is an alternate notation for vector line integrals. So, using the exact same setup as we had on the other page, if our vector field has components f1, f2, and f3, we can go ahead and write this in this format here. This can be confusing because sometimes you only see it presented to you like this, and this can confuse first-time learners of this into thinking it is a scalar line integral. But a scalar line integral has ds. ds, not dx, not dy, not dz. It has ds and ds alone. So what do I mean? So here's an example. The integral over some path c, which I don't care about, is, let's go ahead and say this is minus 4 dy plus 7xy cubed dz. Okay, let's go ahead and go backwards and write it in this format. This would be the integral over c f dot dr, but what's our vector field? Our vector field, there's no dx here, so that means the x component must be 0. The y component, dy, is negative 4. And whatever's in front of the dz, that's our z component. So zxy, so 7xy cubed. That is our vector field. So just be aware of this difference in notation. It can definitely cause people to stumble.